Hi and welcome to this Leaving Cert Higher Level Maths video. In this video we're going to work through Revision Worksheet 13 and this worksheet focuses on Paper 1 Section A. Question 1 is an algebra question and it's worth 30 marks. So part A is find the set of all real values of x for which 2x squared plus x minus 15 is greater than or equal to 0. So we have a quadratic inequality here. So we can see these quadratic inequalities come up like this, but they're also the result of rational inequality, so where we have a fraction, and modulus inequalities, where we have those absolute value or modulus lines. The first thing that you need to do is you need to write it down as an equation. Effectively, we're not able to solve the inequality. We have to instead focus on the corresponding equation and find the answers or the roots for that and use those to get our inequality answer. So I'm going to use guide number. In most cases, guide number will be sufficient for these questions. However, you can always use minus b. There's no problem at all. So here we have a plus 6 and a minus 5. So 2x squared plus 6x minus 5x minus 15 equals 0. 2x is common, leaving me with an x plus 3. Minus 5 is common, again leaving me with an x plus 3. And I get 2x minus 5 x plus 3 equals 0. 2x minus 5 equals 0, which gives us x is equal to 5 over 2, or 2.5 if you prefer. And x plus 3 equals 0, which gives us x equals minus 3. Now, a lot of students stop here, but you haven't answered the question. You've solved this quadratic equation, but we had an inequality to begin with. So we really need to focus on that. So how we go from the equation answers, or those roots, to our answer for the inequality is we use a sketch. So here is just a very rough sketch of a positive quadratic. So it looks something like this. Here is my minus 3. Here is my 2.5. The inequality we want to work with is 2x squared plus x minus 15 is greater than 0. And that's the important part. Greater than 0 means where it's positive. And we're talking about where the function is positive or where y is positive. So we're talking about above the x-axis. So we're looking at these two pieces here. Now on my graph, that relates to this section and this section here. So in terms of my x's, the left hand side there is where x is less than or equal to minus 3, and here it's where it's x is greater than or equal to 2.5. Now we have two distinct parts on our graph, so we're going to have two distinct or two pieces there in our answer. Part B of this question asks us to solve the following simultaneous equations. So here we have a linear, nonlinear. So equation 1 is nonlinear, equation 2 is linear. So the process here is to take the linear, so a plus 2b plus 1 equals 0, and isolate a term. Now it's going to be easier for us to isolate the a since it has no coefficient or a coefficient of 1. If you want to isolate b, you will end up with a fraction. So now that I've isolated a term, I go back to my nonlinear, and everywhere where there's an a, I'm now going to sub in my minus 2b minus 1. So I get minus 2b minus 1 squared minus 2b minus 1 times b plus b squared equals 3. So squaring this out, I can use my shortcut, square the first, 4b squared, twice the first by the second. Just watch your signs here. So plus 4b, square the last, plus 1. Here, it may be easier to write this as minus b times minus 2b minus 1. Remember, the order of the multiplication doesn't matter, so if it's easier for you to write in a particular way, then do that. So while we're doing that multiplication, I'm also going to add these b squareds. So I end up with 5b squareds. I'm also going to tidy up, I've nothing else I can tidy up right now, so I'm going to have a plus 4b plus 1, and then I multiply the minus b by this bracket. That gives me a plus 2b squared plus b, and I'll bring that 3 over, so minus 3 equals 0. That gives me 7b squared plus 5 b minus 2 equals 0. Now we have a quadratic we need to solve. Usually in questions like this, the quadratic, we can use our guide number, and that's the way I'm going to work. But again, if you prefer, you can use your minus b formula for these. So minus 14, and that's a 7 and a 2, so plus 7 minus 2. So I'm going to move up here to finish that. So that gives me 7b squared plus 7b minus 2b minus 2 equals 0. 7b is common, b plus 1, minus 2, and again b plus 1 equals 0. So that gives me a 7b minus 2, and b plus 1 equals 0. That works out either 7b minus 2 equals 0, which gives us b is equal to 2 over 7, or b plus 1 equals 0, which gives me b equals minus 1. So I go back now to the linear equation, but I go back to where I isolated the a. That's going to be the easiest one to work with. So all I'll need to do is sub in my b, and I'll have my answer straight away. So here a is equal to minus 2 times 2 over 7, take away 1. That gives us a is equal to minus 11 over 7, and then I generally would suggest that you write these as points. So if you don't have an x, y, like here in AB, write them in alphabetical order. And then over here, when b is minus 1, we get minus 2 by minus 1, which is minus 1. So minus 2 by minus 1 is plus 2, take away 1. So a is equal to 1. So that point is 1 minus 1. So question 2 is a complex numbers question, and again is worth 30 marks. So given the following information, label the complex numbers Z1, Z2, Z3, Z4, and Z5 on this argand diagram. Now, the information we've been told is Z2 is equal to Z bar 1, which basically means it's the conjugate. So the conjugate, we need to think how that would relate in the graph. When we take a conjugate of a complex number, we change the sign of the imaginary, but the real part stays the same. So effectively what happens, it becomes a reflection through the x or the real axis. So remember, here's my imaginary axis, so the imaginary part is z, and here's my real part of z. So another thing I find is helpful is when you actually connect them back to the origin. So here are my two complex numbers, and it might be easier for you to see that these two are a reflection of each other through the real axis. So one of those is Z1 and one of those is Z2. Now we don't know which is which at this point, so we need to keep going. But I know that this is either Z1 or Z2, and this is either Z2 or Z1, depending on what the rest of the information tells us. So I've used this. It then tells me that Z3 is I times Z1. Now, when you multiply a complex number by I, it's rotated 90 degrees anti-clockwise. So let's look at some of the next complex numbers we have on that diagram. So here's our next one. Well, hopefully you can see straight away, well, actually that makes a 90-degree angle with this complex number here. So what we actually have is this must be Z3, so therefore this is Z1, which means that this one here is Z2. So that's actually solved 3 of our points. I know we knew kind of which the other 2 were. So now I have my Z3. So that's used. Now the final piece of information, and here we have actually got 2 left, but the final piece of information says Z5 is equal to Z3 plus Z4. So we know what Z3 is. So I have 2 remaining, so I'm just going to draw in those 2 lines. So one of these is when I add Z3 plus another complex number. So if we think where Z3 is, it has a positive imaginary and it has a negative real part. So if I was to think of adding it to this point here, just say for example that this was Z4, I don't know at this point. If I was to add them, because they're both in the same quadrant, effectively my answer would end up with a bigger imaginary part, because I'm adding a positive plus a positive, because for this one it's also positive imaginary. But for the real part, it will get smaller. And what I mean by smaller, it's like a bigger negative number. So if it was like, say, this was -2 and this was -3, then my result will be -5. So this seems like it works, because if we think about this Z3 plus Z4, it would lead us to a Z5 up here. If I were to add this point here, so let's get rid of these for a sec. So if I was to add this point to this point, we'd end up with something much longer. So it'd be further up here somewhere when I add the two together, and we don't have that point. So therefore, if we go back, what we had the first time was correct. So this one is Z4, leaving this one as Z5. So it's really important that you understand how complex numbers relate to each other on the Argand diagram, as well as being able to work with them in problems. So part B asks us to use binomial expansion or otherwise to expand this fully. So cos theta plus I sine theta all to the power of 3. Now the or otherwise means that you could do cos theta plus I sine theta times cos theta plus I sine theta times cos theta plus I sine theta. Now that's going to be quite long and tedious, and I suppose you're working with sines and causes, so you have to be really, really careful, but it will work. If you can even go, I suppose, a step further, make life a little bit easier by using maybe the shortcut for squaring it here, that will help. But I'm going to focus on actually using binomial expansion. Either way, you should end up with the same answer. So this is my binomial expansion that we have on page 20 of our log tables. And what it tells us to do is we have n choose 0, n choose 1, n choose 2, where n is the power. So I have 3 choose 0. Now, if it helps, so here is what I'm focusing on. So my x, my y, my n. So here's x, here's y, there's my n. So my first one is n choose 0, x to the power of n. So cos theta to the power of 3, which is cos cubed theta. Plus n choose 1, so 3 choose 1. X to the power of n minus 1, so 3 minus 1 is 2. So that gives me cos squared theta, and then times y. Now y does include an I, so just be careful to make sure not to drop that I. It's very important. Plus the next one is 3 choose 2, and then it's x to the power of 3 minus 2, which is just cos theta. And then we have I sine theta to the power of or, so that's to the power of 2. Plus last one, 3 choose 3, I sine theta to the power of 3. So let's go with our binomial coefficients here. 3 choose 0. This one here is 1. 3 choose 1 is 3. 3 choose 2 is 3. And 3 choose 3 is 1. So I end up with cos cubed theta plus 3. I have an I, so I'm going to pull that out in front. Cos squared theta sine theta plus 3. Now, when I square an I end up with, well, let's put it in as an I squared for the minute, but I'll be changing that to a minus 1. I then have cos theta sine squared theta plus 1, which I don't need to put in, I cubed sine cubed theta. So I do need to go and clean up that I cubed and that I squared. So remember, we should never have I to the power of anything. We can always simplify it down. So I end up here with cos cubed theta plus 3i cos squared theta sine theta. I squared goes to -1, so that gives me a -3 cos theta sine squared theta. And I cubed is like an I squared by an I, so we get -I sine cubed theta. So if you really don't like binomial expansion, you can of course work it out the other way, but you should end up with the same answer. Obviously, working out the long way, it's more prone to error, so just be careful. So part 2 of this says hence or otherwise prove this identity. Cos 3 theta is equal to 4 cos cube theta minus 3 cos theta. So it says hence, which means you're going to use what we worked out in the previous part, and that was an expansion. So we expanded cos theta plus I sine theta all to the power of 3, and this is what we ended up with. Cos cube theta plus 3i cos squared theta sine theta minus 3 cos theta sine squared theta minus I sine cube theta. Now, we can also expand that using De Moivre's theorem. So using De Moivre's theorem, we could work that through as cos 3 theta plus I sine 3 theta. And given that they're both expanding to the power of 3, equating these will give us this little equation here. So cos cube theta plus 3i cos squared theta sine theta minus minus 3 cos theta sine squared theta minus I sine cubed theta is equal to cos 3 theta plus I sine 3 theta. So you might look then and say, well, where do I go from this? Now notice how the identity has no i's. Now that's not to say we just ignore the i's, but we are going to break the equation we have down into two parts because we can equate the real parts and the imaginary parts. So the real terms, we have cos cube theta minus 3 cos theta sine squared theta is equal to cos 3 theta. And in the imaginary parts, or the imaginary terms, we have 3i cos squared theta sine theta minus I sine cube theta equals I sine 3 theta. So going back to the question, you need to look at the real terms and the imaginary terms and figure out, well, which one is it more likely to be? And the answer is going to be real terms because we have that cos cubed theta. So straight away we have that. That's perfect. That's exactly what we wanted. And it also has a cos cubed theta, which is good. Now I know we have 4 of them in our answer, and we have a cos theta here. So that seems like the best one to use. The imaginary ones, it has a sine 3 theta, so it's not exactly what we want. So let's focus on those just real terms. So here are my real terms, and I need to focus on, I've just flipped it. So my left-hand side is perfect. So I need to focus on that right-hand side and making it look like this up here. So what I'm looking at is, well, what do I have versus what do I want? So the cos cube theta is good. The cos theta is good. Okay, my number is, the 3 in front of it is good. I suppose the big problem really is that sine squared theta. And I'd love to get rid of it because it's not in the answer I want. So what could I replace it with? And I want to just focus on keeping it in causes. So I'm going to go to page 13. I'm going to use this little formula here, this little identity. And you might kind of go, well, how do I work with that? But we can rearrange it. So I'm going to replace sine squared a with 1 minus cos squared a, which in terms of our question means 1 minus cos squared theta. So I end up with cos 3 theta is equal to cos cube theta minus 3 cos theta 1 minus cos squared theta, multiplying that out. Remember, my left-hand side is fine, so I'm going to just leave that for the minute. And I get minus 3 cos theta plus 3 cos cubed theta. I can add these together, so I have 1 of them and I add 3 more, which gives me 4 of them, cos cube theta minus 3 cos theta, which is exactly what we were being asked to prove. Now, you don't have to work with this. This is probably the easiest and most efficient way to work. But if you do any kind of substitution in there for that sign, excuse me, for that sign squared, it will be longer, but you will be able to work back to what you want. So question 3 is an integration question worth 30 marks. So the graph of the function g of x is e to the power of x, where x is an element of the real numbers and is between 0 and 1 inclusive. It's shown on the diagram below. On the same diagram, draw the graph of h of x is equal to e to the power of minus x, where x is an element of real numbers in the domain, so x is between 0 and 1 again inclusive. So what we're going to do is we're going to make a little table and we're going to sub in the values that are being used. So you can see the dots along this g of x. It's subbed in 0, 0.2, 0.4, 0.6, 0.8 and 1. So here's my little table. All I've done is I've taken my h of x is equal to e to the power of minus x. I've subbed in my values for x and I found my values for y. Now I've gone to 2 decimal places. You can go to more, but we can only be so accurate. To do a little bit of a drawing, this is what we end up with. So here we can see there is my h of x is e to the power of minus x. So that's what it should look like when you go along and plot your points. So there's my points there. So part B then says find the area enclosed by g of x is equal to e to the power of x, h of x is equal to e to the power of minus x, and the line x is equal to 0.75. So let's put in that line first. So we have it there in orange. So this is x is equal to 0.75. So there's my h of x. It's equal to e to the power of minus x. So what we're basically looking for is this area here. So once you want area with a graph, we're going to be talking about integration. So we want to integrate between where those two graphs meet, which actually is fine because it's where we started. So that is where x equals 0. And then on the right hand side, it's bounded by x is equal to 0.75. So that's what we end up with. We want to integrate g of x minus h of x between 0 and 0.75. And it looks like e to the power of x minus e to the power of minus x. When we integrate that, e to the power of x doesn't change. E to the power of minus x ends up divided by the coefficient or divided by the derivative of that power. So it's divided by a minus. So we end up with a plus e to the power of minus x. We're going to work that between 0 and 0.75. And when we do that, we end up with 0.589. Question 4 is a functions question worth 30 marks. So the diagram shows the graph of the function g of x is equal to the square root of 4x minus 3. State whether or not g of x is injective. Give a reason for your answer. So for injective, we use the horizontal line test. And as you can see, a horizontal line drawn will only touch the graph once. So it is injective. Be really, really clear in answering your question, because sometimes in a question like this, so as we get so many different types of questions on injective, make sure you're clear what the question is and make sure you answer it. They've asked, state whether or not it is injective. So you want to be able to turn around and say, well, g of x is injective. The reason is it passes the vertical line test, but if for the horizontal line test. So a horizontal line touches the graph only once. So we say at most once. So it's okay if it doesn't touch it at all, and there is areas in the graph, or there are areas in the graph where that will happen, but as long as it doesn't touch it more than once, so at most once, then we're good for injective. So part B then says, under what criteria is g of x bijective? So bijective, remember, means it is both injective and surjective. So injective and then surjective. Now, we've already kind of told the answer, or well, we've already looked at part A saying yes, it was injective. The next thing to look at, well, is it surjective? And the answer is no. Surjective is where your range equals your codomain, so where all the y values are used. Now here, the y values aren't used underneath the x-axis because of the square root. Remember, the square root, this basically means positive square root, so we were only taking positive answers. So the reason it's not surjective is you've all of these values down here on the y-axis that are not being used. So because they didn't tell us anything about the codomain, okay, it just says g of x, the domain will then be or, all the real numbers, and the codomain, so possible y values, will also be or. So how do we fix the problem with surjective then? Well, if we limit this graph and specifically limit the codomain to only including those values of y we use, so get rid of all of these down here, well, then it'd be fine, because now we are only using the y values which can be used. So if we think of it in terms of the range of the function, the range was y is greater than or equal to 0. So we want to force the codomain to be the same. So y is greater than or equal to 0. So now the range and the codomain are equal. We now have a bijective function, or at least we have a surjective, and it was already injective. Another way we could write this range and codomain is to use our brackets, so 0 to infinity. So remember, when you're using infinity, to use that round bracket, which means that value is not included. 0 can be included. So here then it's like, well, what would be the values, or what domain would this be? So given where we're at, we could also cut the domain, the x's, so that we start here. So let's limit the domain as well. So that means we won't be adding in any numbers before that, because we're going to get an error anyway with this square root. If we go too far or we make that x too small. So what I really need to know is, what is this point here on the x-axis? So that point happens when the y is equal to 0. So where the square root of 4x minus 3 equals 0. So where 4x minus 3 equals 0, or 4x equals 3, or x is equal to 3 over 4. So the domain that we want is basically where x is greater than or equal to that value. And again, we can use our brackets, 4 to infinity, to do that for the domain. So under what criteria is g of x bijective, i.e. for what domain and codomain does g of x meet this criteria? And that's what we have. There is my domain, there is my codomain. So here are my two answers, domain and my codomain. The last part of this question then asks us to find the inverse of find the inverse function g inverse of x, sketch the graph on the function in the diagram below, and hence explain how g of x and g inverse of x relate geometrically to each other. So let's find the inverse function first. So we start with y equals square root of 4x minus 3. And we want to isolate our x. So the first thing I need to do is square both sides. That way we get rid of the square root. So then we have 4x is equal to y squared plus 3. Divide both sides by 4. And we get x equals y squared plus 3 all over 4. We then rewrite that as g inverse of x. We change our y to our x. And that is finding my g inverse of x. So I have done the first part of that question, find the inverse function g of x. The second part then asks me to sketch it on the graph. So in order to sketch it, we need this line here, which is the line x equals y. This is the line that goes through the points 0, 0, 1, 1, 2, 2, 3, 3, and so on. And what we want to do then is create the mirror image of it through that line. So we end up with something like this. So this is my g inverse of x. And then the last part of this question was hence explain how they relate geometrically to each other. So G inverse of x is the reflection of G of x under axial symmetry through the line x equals y.